Hello everyone, this is a trig identities lesson which will not be discussed in too much detail in class due to the lost time we have. I told you before that when you find the sine of an angle to be, let's say, 1 over 2, that means you can flip that to find the cosecant of theta to be, in this case, 2 over 1. Now what this means is that the cosecant function is the reciprocal of the sine function. And today's lesson is going to build on something along those lines. Right? We have 7 trig identities here. First is that cosecant is equal to 1 over sine. Second is that secant is equal to 1 over cosine. And third, which I didn't tell you, which I will elaborate on a little bit, tangent is actually equal to sine over cosine function. And since the cotangent function is the reciprocal of the tangent function, that makes the cotangent function able to be written as cosine over sine. Another function that we have, which I can prove for you if you ask in class, is that sine squared plus cosine squared equals 1. This is called the Pythagorean identity. Right, that means if you see a sine squared plus cosine squared anywhere, you can simply replace that with the number 1. And if we were to subtract the cosine squared from both sides, that would get us identity number 6, right? So really 6 and 7 are offshoots of number 5 over here. We could subtract the sine function from both sides, and that will get us this 7th identity, cosine squared is equal to 1 minus sine squared. So we're going to use these identities today, but first I want to elaborate a little bit on this tangent function. All right, we looked at the unit circle for the past couple of days, and no one has raised an issue, but notice that the unit circle only tells you sine and cosine values. It does not tell you tangent values. That's because it doesn't really need to. We can use this identity, tangent equal to sine over cosine. So if we're looking for the tangent of 60 degrees, or let's use something that's not doable on a 30, 60, 90 right triangle really, let's look at maybe the tangent of 210 degrees. Right? From our knowledge of ASTC, we know that this is going to be a positive value, but this means that the tangent of 210 is equal to the sine of 210 divided by the cosine of 210. So we don't need to actually calculate opposite over adjacent and all that business. If we can find the value of the sine of 210, which is going to be negative 1 over 2, and we can also find the value of the cosine of 210, which by the unit circle is equal to negative radical 3 over 2. That means we can calculate and reduce this complex fraction to be negative 1 over 2 times negative 2 over radical 3. Right? That's by dividing numerator divided by denominator, and then using keep change flip. Cross canceling allows us to cross out these 2's. So we are multiplying negative 1 times negative 1 over radical 3, which is equal to a positive 1 over radical 3. And if you were to use a 30-degree reference angle in the third quadrant and find opposite over adjacent in that sense, you would get the same value. Right? So that's how the unit circle incorporates a tangent function. So let's start using these identities. Right? Using these identities, again here, numbers 1 through 6, we have all of them at our disposal. We can prove that these identities here, we can prove that these sides here are actually equal. Tangent squared x plus 1 is equal to secant squared x. Some word of advice on doing these types of problems. Tangent squared, turn this into a sine squared over cosine squared. I'm going to ditch the x part because it doesn't really matter for these types of problems, but technically they should be there. Now, if you're replacing tangent with sine over cosine, that means you can replace tangent squared with sine squared over cosine squared. And a general word of advice, the very first step should be, when you are simplifying these, when you're trying to match up the left side and the right side, try to turn everything into either sine or cosine. Right, and based on these first four identities, cosecant's equal to 1 over sine, secant equals 1 over cosine, tangent is sine over cosine, cotangent cosine over sine. That means that each of the four trig functions that are not sine or cosine can be written as sine or cosine. Tangent squared is going to be sine squared over cosine squared. Secant squared is going to be 1 over cosine squared. So let's look at the left side. It looks a little more complicated because it has two things added together. Sine squared over cosine squared plus 1. Let's get a common denominator to add these fractions or these terms together on the left-hand side. That common denominator is going to be cosine squared. Sine squared over cosine squared plus cosine squared over cosine squared is what this becomes. And on the right-hand side, we can keep it as 1 over cosine squared because we can't really simplify that any further. Combining these two fractions, we can get sine squared plus cosine squared over one single cosine squared. And remember, the Pythagorean identity said sine squared x plus cosine squared x is equal to 1, which means that we can take this sine squared plus cosine squared and replace it with the number 1. So the left side reads 1 over cosine squared, and the right side reads 1 over cosine squared also, and we know that the left side and right side are in fact equal. Right, this equality is not proven until the left side and right side are 100% exactly the same. And if you need to simplify both sides in order to do that until they meet, that's totally fine. Let's look at this one. Verify. Tangent squared x minus sine squared x equals tangent squared x times sine squared x. Okay, once again, the first thing that we can do is replace everything that is not in sine or cosine form and put it into sine or cosine form. That's going to be sine squared over cosine squared minus sine squared. Once again, ditching the x's. This is equal to sine squared over cosine squared times sine squared. I'm leaving some space because, again, I do want to combine like terms over here with a common denominator of cosine squared. So I'm going to multiply that sine squared over 1 with a cosine squared over cosine squared. Over here is also sine squared over 1, so we can multiply these fractions together. So we're going to get sine squared over cosine squared minus sine squared times cosine squared over cosine squared. And on the other side, sine squared times sine squared over cosine squared. Now I can multiply these together to get a sine to the 4th power x, but I actually don't want to because I don't need to. So moving down, we can combine these two fractions because they have the same denominator. Sine squared minus sine squared cosine squared over cosine squared in one single fraction. Sine squared times sine squared over cosine squared as a single fraction. There's not much simplification to be done here because, again, everything is in our sine cosine base values. Up on the numerator, sine squared minus sine squared cosine squared. This is factorable by greatest common factor. There is, in here, a GCF equal to sine squared. So that's going to become sine to the 2nd power, and in parentheses 1 minus cosine squared, right? Because we are factoring a sine squared out of these two terms. And their denominator is cosine to the 2nd power equals sine squared times sine squared over cosine squared. Now take a look at our Pythagorean identity. Right? The initial Pythagorean identity says that sine squared plus cosine squared equals 1. But if we were to subtract sine squared from both sides, that would get us that cosine squared. If we were to subtract cosine squared from both sides, that would tell us that sine squared is actually equal to 1 minus cosine squared. Right? Those two are the same, which means they can be replaced with each other. Since this over here says 1 minus cosine squared, that means we can replace that with a sine squared. And the left side and right side match up. This verification is done. We have proven that tangent squared minus sine squared x is equal to tangent squared x times sine squared x. Right? They are in fact the same thing. Let's do another one that starts off with fractions here. 1 over the tangent of x plus the tangent of x. Now if we are strictly following the rules of turning everything into sine and cosine, we're going to get 1 over sine over cosine plus sine over cosine equals sine 1 over sine times cosine. Right, the right side is actually not going to change at all because it already is in sine cosine base values. Over here we have a complex fraction. Right, the numerator is equal to 1, the denominator is equal to sine over cosine. So that's 1 over 1 times cosine over sine when we apply our division rule and then keep change flip. Right, we are flipping the bottom fraction. Plus sine over cosine equals 1 over sine times cosine. Now this is equal to cosine over sine plus sine over cosine, and that's going to equal 1 over sine times cosine. Right, all we did here was multiply this cosine over sine times 1. Didn't really do much there. So again, fractions. We're looking to make two fractions, add them together to get one fraction, and hopefully that one fraction will be the same as what we have on the right-hand side. So that means we're going to have at least common denominator here, which is sine of x times the cosine of x. Which means that we need to multiply these values for each of these individual fractions in order to make these denominators the same, this one right here. So we're going to get cosine to the second power over sine cosine plus sine to the second power over sine cosine. And then 1 over sine cosine on the right-hand side. Combining these fractions together now, because they have a common denominator, cosine squared plus sine squared is equal to, cosine squared plus sine squared over sine cosine should equal 1 over sine cosine, and in fact they do. Sine squared plus cosine squared, addition is commutative, so in any order it still is equal to the number 1 over sine of x times the cosine of x. I'll put those x's back in. Right, it's a lot of writing, so I did not do it before because I am lazy. This checks out, and we have verified this identity. Thank you very much, and I hope to speak to you soon. If you have any questions, please let me know in class.